Okay, so good morning, everybody. Let's get started. So for our first talk this morning, it's a great pleasure to introduce Leonardo Cavenaghi from IMECC. We'll speak about atoms being simple.
Yeah. All right. Thank you very much for attending. Let just me start the clock. So atoms being symbols is going to be more or less figure out the table, but let's see what we can do. I'm going to start first establishing what's going to be my work environment. Then I'll explain what I'll do. Like throughout the talk, we're mainly considering smooth projective varieties of dimensions 2 and 3. Like I don't think there's going to be any other dimension in this talk. We consider this P-cyclic group or addition, right? And we're going to consider like generically 3 regular actions, like automorphism actions on these smooth projective varieties. And here we show them the fixed values for this action on X as X to the power C. All right.
So question, what is a regular?
By automorphisms, meaning like the maps that realize are not just like variational maps, but we did the action. Yeah. So there's a way to determine this block. And we're going to consider this feature locus. And the main idea here is to give equivariant variational geometry talk, more or less. But through the eyes of the combination of 2 key concepts in this field, like for instance, this modular symbols stories developed by Kontsevich-Pestun-Tschinkel. That's why I say symbols. And then the new theory of atoms, recently influenced by Katzarkov-Kontsevich-Pantev-Yu. All right, so we're going to try to merge these 2 concepts to find some applications in G equivariant variational geometry, but in this talk where G are finite group shall be Z. And to begin with, to settle the ground, let's recall some definitions. We're going to say that like 2 smooth projective variables shall be ZP equivalent variational if not only we find a variational map between them, but this map is equivalent with respect to the group actions. Some note on instructions in this section where we have ZP actions is the following. If X and X prime has to be ZP variational equivalent, then if the fixed modulus of one is non-empty, then this non-empty, then necessarily this should hold to the other. Also, there are some criteria relating this non-vanishing homology here, H1 ZP of the car, in the sense that if the smooth projective variety is stably variational, or like a ZP stably variational, meaning that is ZP variational to some projective space after taking the cross product with another projective space, then necessarily this H1 should vanish. So this gives the obstruction. Yeah.
The obstruction one being X, there is no fixed locus, or X prime, there is fixed locus.
I mean, if this X and X prime happens to be ZP equivalent variational, then the fixed locus of both cannot be n. So if one is like n and the other is not, then they cannot be ZP variational equivalent. And in this talk, as we're going to see, we're going to present some magic Z-value formulas obtained from this interaction between atoms and symbols. And these are like guesses from that construction that I did explain. But once you guess the formulas, you want to prove that they did give you some ZP equivalent variational variance. And the way that you do this is relying on this big factorization theory, meaning it's sufficient to check that your presented formula is divided under blocks, where the centers of the equation are divided under the group function. All right, so let's warm up. We start with the statement. We're going to restrict here the case of surface, so we have like surface, and we consider Z2 actions. Then I agree that this Z value quantity is Z2 variational value, where remembering that X to the power X like Z2 is the fixed locus, you compute its other characteristic, and then when you look to this fixed locus, you count all the possible P1s appearing there, rational curves, and it will be empty. But then we look to their normal bundle inside of your variant X, and compute the decrease of these normal bundles. Then the claim is that this Z-bound quantity is a Z2 variational value. Let's see an example. You take this collection surface. We're gonna like take these coordinates, taken in something 3. Now we're gonna compute the invariant to this guy. So we're going to consider an interaction on this. And this interaction shall be induced by simply like you swap partners. And then you check that, well, the fixed locus is given by the equation. And hence, you have 3 fixed points. You have no lines in the fixed locus, like no version of curves. And then the invariant gives 3. This is just like the way that this invariant works. Simple as this. All right. Let's make another. This is not divided. As you can see, like they are more or less symmetrical in some sense. And this relies on the combination of this homology of your surface with also the topological property that is directly of the fixed point set. Now, this statement works for ZP actions for peak time. And the claim is that again, this Z bar divided is the ZP variation pattern. So to check this, you check that invariant on the blocks. All right. And here we take A to be a generator of your cyclic group. Then you look to the induced action in homology, take the superface in homology supervector space, and this one I claim that's ZP variation invariant. It turns out that for P equals to 2, you can mix homological and hence geometric homological and geometric data to build as a equivariant value. It only works for Z2. And the other statement, as you can see, is a corollary to the previous statement, is a corollary of this because you just sum the 2 equations appear here. Okay, but these are like formula where working with surface. The main like result shall be the following, and for the rest of the talk, I'm going to try to explain what are the terms appearing here in this statement, some applications, and how we get these magic formulas. So you consider like a smooth reducible vertical folds equivalent to like regular generic 3 ZP actions, and then you fix a curve, a smooth curve that has genus at least 1. You choose one, all right? Then when you look to the fixed point set of your smooth projective variants, you're going to count the number of components that are isomorphic to your curve in the fixed locus. Because the fixed locus, it contains some smooth variants. In your dimension 3, it will be points, surface, or curves. You have fixed that curve. Right? That's like your choice. Now you count the number of components that are isomorphic to this curve and put this minus sign there. And you count the number of surface, like appearing in your fixed point at the position, that happens to be birational equivalent to C cross Q1. All right? And there is this mysterious part here that's ZP atomic structures isomorphic to perfect complexes with integral functions. I'm going to make sense of this less quantity throughout the talk. Listen.
So, and the choice of C is free, so you're actually a family direction.
Yeah. It is not only one version, but the family that depends on, but each invariant comes with the choice of C. And then it changes. And in each example, as is going to be my last slide, there is a convenient C that you intend to choose to make a solution for this. At this point, the main thing here is for me at least, when you see such a result like this, the first thing that you would like to ask is, how can you guess it's mysterious? Why do they know this would be like a variation now invariance? How can you come get to this conclusion? And whether you why do you have this kind of like dimensional restrictions? And this is essentially related to this perfect complex story here, enhanced atoms, that I'm going to try to briefly give you the idea and into the insight why this thing should work. All right, into that, we make our first intercurves. Let's explain what are symbols per se and how they serve as G variation variants. If you pick a finite group that needs to be a beacon, then you consider the character group of this group. And for n for any choice of like a positive integer that's greater or equal to, the idea is to build a free model, alright, whose generators shall be the symbols here. This is a Tschinkel test. And you're going to choose the symbols, choosing the characters that generate the character. So you have chosen some generators to a certain symbol. Now we're going to use relations to this. The first one is that, well, you want that this choice of n apples, they're not like, they do not see when you deal with permutations of the possible characters. And there is already one like combinatorial formula that is this strange story that relates to choice of generators of the characters group, and then some manipulations here and summation. The main aspect of this combinatorial description of this guy, of this module, is that this choice B, so this even B, this relation, it comes always for, because you want in the end to get to some variational invariant out of this model that you are considering. So this choice combinatorically represents some geometric procedure related to blow-up. Please read.
So what was the first thing with the O relation? What it means?
Yeah, I mean, it should be permutation, but I don't know why it's called. I guess.
Just looking at what this relation means. You're saying besides these things of this.
Yeah, it means so you connect, you connect these couples here. So you have like n characters, right? You just want that no matter like the order of the characters you choose, like if you have like 1, 2, 3, then this should be the same as 3 to 1. It's just like to reduce the size of your group, like in terms of because what really matters are the characters, because the real combinatorics is hidden on the second. So it matters the the characters themselves and the second relation, not the order that they are here. This work apart. It's just this. All right. So then you build this module, and then you like to understand like which groups can serve as these models, right? And a simple example is, of course, I have like you take n equals to greater or equal to 2, but so what happens if you pick n equals to 1 here? So one factor. This has some like number theoretic description. It's simply that if you pick G to be cyclic group, then this Z model that you're building is just Z to the power of PD, where K 5, is the Euler sausage function. Things starts to get more interesting when you pick n equals to 2 and b to be a prime. Then you see that for Z2, there's not much that you can say, but for 3, then you get integers, and starting for p equals 7, then it starts to appear torsion on this model. This is it about this description of these models that we're doing. But how then you relate them with variation invariants? If you pick your smooth projective variety, dimension n greater or equal to 2, this n shall play the role of the group, this model that we're building. You look to the fixed models decomposition. You decompose irreducible varieties, right? And they have a dimension, the dimension of the variety -1 at most. So in the case of three-dimensional smooth projective varieties, this f alpha can be like isolated points, curves, or surface. Then you're going to look to the induced action of the group on the tangent space of each of these f alpha. And then you collect the characters. The characters split the tangent space in this eigenspace, and they're like the eigenvalues for this. Picking these characters makes you to build the invariants. So to each irreducible component, you assign an element on B and G, and then you sum over all irreducible components. Yeah.
Here, G is always fine.
Always find to Avidia, because you have to have this decomposition of the characters. Then you take the sum, and the result of Kontsevich-Pestun-Tschinkel is this is G variational variance, in the sense that how to prove this, you start to making all the possible blowups, and then you realize that the second relation that I have described here are precisely built to make this quantity to be variation value. You see, it's a computation that you make, and then you just choose relations so that you get what you want. Okay. So this is the first chief focus that we did so far. And this more or less gives you some description of what our symbols are. Then Tschinkel-Kontsevich-Pestun-Tschinkel, is like a lot of this theory, and after this Tschinkel and concept fresh, also many others. And this kind of reasoning is very successful to try to understand obstructions in variational geometry. But still, part of this description, there are some smooth projective variants with functional functions that you cannot say much. The idea in the combination with this Apple's story is to produce some kind of refinement to this. And get that variants that I presented. To that, I will quickly recall this epsilon under composition. I just put this slide here to the ones that work in Ludwig's and Tom's talk. I will try to make a different perspective on this quickly. But atom theory, to my understanding, and I ask Tom permission to say this, that is just a formalist that comes with choice of homology theory and so view homology theory and non-partake right through actions on this homology theories. And but I mean, these are not like their characterization, they're formalism to understand something that is deeper. And this is like how you do in practice. You pick your some projective variants, you have quantum multiplication, you have either vector field, spectral cover, and the atoms are connected components. The main point is that when you do blow up, you know how to relate these atoms, meaning these connected components of the reduced cover of the original smooth projective variants and the center. But let's make an example in practice of how this things should be completed. And then I'll try to put a perspective, because I said that we treat this and appear in the formula as perfect complexes. What do we mean by this? And this should be the thing that you should keep from the start. To present an example, we pick a Y to be a final manifold, then you choose ample vector bundle on Y. You choose its rank there, and then you can choose like some section such that the preimage of the zero shall be a smooth final section. Then you look to this preimage seeking inside of Y, and then you have ambient homology, then you have the complement of the ambient homology with respect to pairing. One information is that this complement of ambient homology will sit on this X and this X stuff, and then this result of summated and combination of summated and hard latches is that if you pick any K that's like strictly lesser than the X, the dimension of your X, then this guy here is isomorphism, and have also this isomorphism, but the induced mapping homology is rejected for a K different from the X. How do we use this to compute these splitting homologies that are supposed to be these atoms? If you pick Y to be P to be Y, then you choose this as your ample vector bundle. And the result is that for this small quantum multiplication, the spectrum as a set on your X, that's the section, the image of the zero coming from the sample vector bundle. This is the zero and some roots of unity. Okay? This is the spectrum as a set. So disregarding multiplicity. This is how we do like in practice. And then when you look to the homology, for instance, if you pick X to be the complete intersection of two quadrics, then what these eigenvalues are telling you is that the eigenvalues corresponding to roots of unit shall form 1D subspaces in this homology. And there is the zero eigenvalue whose generalized eigenspace shall correspond precisely to each three of X. And this is what is giving you this kind of splitting that I said about like homology in relation to this quantum multiplication. But this is like how you do this in practice. This shall not be needed in this talk. What shall be needed is why there was some perfect complexes and how this related to these mysterious atoms. And to talk about this, we remember to you that we taught you that if X is smooth projective variety, we can define this Hodge homology. And if you consider, for instance, the category of bound-derived quadratic sheaves, you have a similar orthogonal decomposition, and you can, this is a statement, the Hodge homology of derived category of quadratic sheaves shall be related with the Hodge homology of the species in the SOV. So what you want to understand is that you treat your space, your smooth projective variety as non-computative space by choosing some category, and then there should be some similar orthogonal decomposition, for instance, for the derived category of quadratic sheaves, such that the Hodge homologies of the elements there should be your atoms. This is what I say here. To understand this talk, you're going to think about perfect complexes, or the derived quadratic sheaves, and the Hodge homologies. So you're going to treat your smooth projective variety as a non-computative space by taking the derived category of sheaves. Then, like in practice, you choose view homology theory, construct this which is going to lead to the north median F manifold, not going to solve. But the expectation is that there is some SOV for the derived category of X, such that when you take this periodic homology, this shall correspond as non-computative structures to these atomic pieces, meaning the guys that I completed in that example. So that's why in that statement I have perfect complex, because we are looking to these categories instead of like doing all this machine learning practice. All right. This is all I want to say about atoms. But if you want to keep something in mind, just think about it's sufficient to think that for results in this talk that you are looking to these categories. And that's why it appears perfect complex on this form. And of course, when you have like smooth projective varieties with group actions, you can use action on these categories. And when I say trivial on that statement, that I shall go back again. Whoops, sorry. Perfect complex with trivial group actions, this should play the role of like fixed atoms under group action. So this is a statement about quantities that are fixed on group actions, both coming from like the varieties, but also coming from this category aspect. Okay. So then these are like these two ingredients, and we want to merge them to get something. How do you do this? You're going to build as a model in the same way that Kontsevich-Pestun-Tschinkel did. But now the generators shall come from two different natures, both geometric and symbolic, but also atomic by the use of the categories and group actions. So to symbols, you're going to choose these elements. That's going to be these triples of, and remember that this group of B3G, it only has to do with variation geometry if you assign a right to the perspective quantity there. But as an entity itself, it exists as a module, and then you can pick these elements, which geometrically they will correspond to symbols whose action, so like for fixed points, whose action on the tangent space gives you that characters. This shall be one generator. Then you're going to take what? Like verbs, and the pairs consisting of verbs and some characters on the group character. And that this intends to correspond to irreducible components of the fixed point set that are P1, isomorphic P1, and the numbers appearing shall be the characters for the representation on the normal bond. Obviously, you also like keep track of the curves with higher genus, and hence like their normal bundles, the characters in the normal bundles, and you do this for class of surface. But then in the surface as generators, you collect only variational type of surface. So you collect the variational surface, then you have this normal bundle sitting inside of the three-dimensional projective variety. You have only one character in the normal bundle, and this shall serve as A1. Now, lastly, you collect these atoms in the heap. Because to each smooth projective variety, you can associate this decomposition homology. And now what we will do to define this set is, well, let's consider all the possible isomorphous type of smooth projective varieties and all the possible decompositions in homology that appear. Then you like mod out by these blowout relations and also to this quantum relay here. But if you like to think, what you have to collect are like what are the possible perfect complexes of like points, curves, and surface appearing here, and that's what you're gonna take. So you choose these generators, and now you have to start to impose relations to get like some variation variant properties. Please.
What is the verb to?
Oh, I didn't mention, and but the point is that I only mean that I'm considering the variational type of surface. So curve is the stands for this bird side group, and that collects variational type of in this case because it's two the surface. So the point is that this is one generator related to surface has to be variational classes. This is not indicating curves. Okay. And then you have this collection, and you have to find relations. This next slide shall be like a bit scary, but I don't want to go. This is just to scare indeed. That's why the relations are like these are only two, like the possible relations. There are many that have to keep track of them. But it's just to show that you don't need to pay attention to this. But if you look to this like before the lesson, this is where you have the curves. It starts to appear some quantities that we have in our formula. So this is more or less the reason to guess that you want to send the relations to be zero on when you map your Z model to Z. But let's not pay attention on this. Let's understand how you can obtain this kind of relations when you have your symbols, right? And when you have your symbols and your atoms, so how to derive these relations? To do that, you first look to the decomposition of the fixed point set. And the main thing that you need to know is what happens when I start to do like these equivariant blowups. Does the Azad make contributions to the fixed point set? If so, how does how it is done? And the thinking about the characters is that if you blow up, then you get a solution divisor, there's a projectization of the normal bundle. Then you have to understand how the characters appear in the normal bundle, because this will give you the invariant space that when you projectivize, this you will give the possible fixed points appearing in the blow-up. And that's how you relate that symbols with the characters appearing. And regarding atoms, you have like a Orlov semi-orthogonal decomposition formula for the blow-up. So it tells you how these blow-ups will appear upstairs and how they are compatible with your functions and certain deduce the trivial functions. In like a more complete example, let's take Z. Remember that we are in the three-dimensional case to serve that shall be curve that will serve as a fixed point set component. Then, because you're in dimension 3, when you look to the G representation on the normal bundle, you have two parameters, right? Say A1 and A2. If A1 is different from A2, when you blow up, then you look to this invariant space. When you projectivize, it will appear two copies. So yeah, let's see. The blow-ups are resulting in two copies of Z appearing in the blow-up because you have like the original Z and the one coming from the verticalization. If they are equal, what we introduce as new fixed component in the blow-up is something that is variation equivalent to your curve Z times P1. So in a picture it's like this, you have the normal bundle, you have this axis that shall be line bundles, Then when you projectivize, if they correspond to distinct characters, you get indeed Z unit of Z. But if they don't split because they're the same invariant space, when you projectivize, you gain something that's variational to Z cross P1. Then you keep track of all this information on the clause. You keep track of them because now you know not only the variational factors on this class, but also how the characters related to this story, but how they will influence on the chains coming from the symbols and the hence atoms as well as generators. And you keep tracking of this, and this will give you the relations so that in the end, the expectation is to get some new G variation of line. So I said that that formulas, at least to me, on the statements of the results, they are what call as mysterious. But they serve as like some kind of factory to make many new Z-value values. And the way that you do this is really by hand, but there is no deep meaning in the sense of the way that you establish the results. For instance, let's guess one of our formulas in a complete example. This is just guessing. Again, a posteriori you have to prove that indeed this given variation it's made to give. So you pick G to be Z2. All right. So the 2 is quite simple group. Then the only possibility for a character should be 1, because we don't want 0 character. Because we have genetically free actions. Then from the one side, what are the generators? From the atom side shall be perfect complex of curves with trivial Z2 actions. And then remember that I said that we have to choose a curve in the beginning. So now choose a curve. Let's describe what are the generators for this choice of curve. Shall be the perfect complex of this curve with trivial action. Right? Now, from the symbol side, you take the pairs consisting of the isomorphous type of the curve, if possible characters. And to the surface, the variational type of C cross Q1 and a possible character. Now, the main point is that one of our relations is precisely this, perfect complex with trivial fractions. Then either you subtract 1, so the curve and character is 1, 1, because we will only have this possibility 1 as an actor. And this term sum for surface. Oh, there is no term sum from surface at all. But this guy here stands to a relation. So when you map to Z, this should correspond to 0 under your homomorphism from your Z model to Z. And just to recall to you that this shall appear as one of the relations. So, for instance, it's minus CAA is appear as one of the relations. I'm just describing one possible relation when you choose an isomorphous type of the curve. So this thing here, you want to make it to 0, so you want it to 0, right? So the both of them, so 0 and 0. Now you start to attribute some weights to this symbolic generator, Z value weights, so that when you sum, you get 0. Then you say, well, that generator that corresponds to C11, you attribute the weight 1. Then this C cross Q1 with 1, you attribute the weight -2. And to perfect complex, you attribute the weight -1. Meaning you choose homomorphism with Z, and you're saying this element goes there, this element goes there. And then they sum to 0. But now you start to realize, well, what is this saying? So I have components of curves, right? And everywhere they have like the weight 1. For the surface, they have the weight 2. And to this perfect complex is 1. So when you have a formula such as this, you can guess. I minus the components, because we attribute the weight 1 to components that are isomorphic to curve, minus 2 the components that are variational to C plus 1, because we have assigned there minus 2, and then plus Z2 atoms that are isomorphic. That's how we get the formula. As simple as this. You start attributing Z value to the generators, and then you have to know that they go to 0 in a relation. There is invariant. And then related to the question is like, you have many possible invariants, right? Indeed, you have many possible invariants, just because you have many possible relations. And then the point is that to choose what relation shall be used as invariant that shall be useful to your possible applications. But it's simple as this, and it's made to work. When it comes to proofs, now that you have guessed, you just verify like that's invariant under this ZP equivalent clause. It's just this. All right. And because this is atoms with symbols, so we have to provide an example of where our invariant indeed gives something new. That's the symbol or atoms itself in the way that one will explain does not give an answer. So you pick a polynomial of degree greater or equal to 4 with only simple roots. Then you consider the right defined by this equation. There is like a very one thing to define this reaction on this variable. That if you pick this x1, x2, and x3, you just like simply fill with them. Turns out that the fixed point set is precisely a curve C that's described by equation like that, x to the cube equals to qy, and it has genus greater or equal than q. What you're going to do then is to look to your smooth coordinate equivalent, you complexify it, extend the action, and there's a way of doing this by this choice of polynomials that adds no new component in the fixed point set. So the fixed locus here is a curve of genus greater or equal than 1. So now, what is the obvious choice for our invariant? Right, so a curve that has genus greater or equal than 1. More like a completely this curve. This is one of the type of this curve. So if you compute properly, the weights for the Z3 normal bundle action on this compactification will be 1 and 2, the characters, and then you collect the symbol class corresponding to it. And there is no atomic generators, and the reason for this is because this variety with no group action, this is rational over C, and its homology is entirely consisting of Hodge cycles. Meaning that's all. For instance, HQQ is 0 if P minus Q is different from 0. So it means that there will be no piece homology that will correspond to the homology of curve with hydrogens. That's why there's no atomic generator related to curves with hydrogens. So then you compute the invariant. It shall be simple than number plus 1. Right, in our formula, because let's remember this the formulas. So for instance, it's a bit far, but it's important that we properly get it. So we have the component which shows the curve to be coincide with that one that appears in the example. So we have minus 1 component, right? So the invariant shall be minus 1. Okay, so you have this component that is one of the curve. There is no surface in the fixed point set. And there is no atom that looks like an atom coming from a curve of hydrogens, because its homology consists purely of that set. Hence, the invariant shall be minus 1, but you can just multiply by minus 1 again, and you get that thing that I said, that the invariant is plus 1. But it happens that regardless of the choice of Z3 linear actions of B3, so you choose any linear action of B3, meaning any Z3 action that comes from the periodization of a representation. This invariant will be 0 because there is no way a curve with positive genus can appear as the fixed point set for linear actions on the first space. And also like that, no surface does birational flow. The curve with higher genus plus to 1. And also the homology of the Z can never have like that. The part of the homology of something that's a curve with higher genus. So this invariant is 0 for P3 with any linear action. And the conclusion hence is that after this quantification, this smooth projective variety cannot be Z3 birationally equivalent to P3 for no choice of linear action. And this is